Let me begin by correcting an equation in the previous slide. So this is A. This should go away. That's a value of A, which is a lambda expansion. Okay, now I was talking about mu dependence of 1 pi, renormalized 1 pi vertices. We need to know what a renormalized 1 pi vertex is, and so on. So let me discuss this. Mu dependence of renormalized 1 pi vertices. We need to recall a few statements. One is that Green's functions are finite when evaluated using modified Feynman diagrams. Right? And then the relation between the 1 pi vertices and connected Green's function. These two things we have to we shall use. The reason why the first point is that is to appreciate that the Green's functions are finite when evaluated using modified Feynman diagrams, because the Green's functions have the definition in terms of the path integral, and then and therefore one has to define the renormalized Green's functions as the path integral that result into the finite values of the Feynman diagrams, and then using the relation between the 1 pi vertices and the Green's functions, one defines the renormalized Green's functions. So that is the approach. So let us first do that. Let me write it down. So quadratic piece of effective action is given by half integral dx dy phi CLx gamma 2 x minus y phi CLy. So that is the 2.1 pi vertex, and this satisfies gamma 2 x minus z times gc2 z minus y is proportional to delta x minus y. This is written in terms of ddp. In the Fourier transformation of that will be given by to the power I p dot z minus y times g tilde to C P square, and this is given by 1 over P square plus M square minus omega square of P square. Okay, so in the Fourier space, the expression for the connected Green's function is this, and the quadratic and the quadratic piece of the effective action from where you get this 2.1 pi vertex is the inverse of that. This is what we saw earlier, and therefore the Fourier transform of this will be Fourier transform of gamma 2 will be given by P square plus M square minus omega square of P square, because it should be inverse of that. And so this is for n equals 2. For a general n, one has a term of this sort in the effective action, 1 over factorial n du1 to dun gamma n u1 to un times phi cl where, so that is the endpoint 1 pi vertex, and the weight is related to endpoint connected Green's function is that connected Green's function will be given by this 2-point function x1 minus u1 to gc2 xn minus un times gamma n u1 to un plus all these tree-level diagrams with lower gamma n's, lower 0.1 pi vertices. But this first line is going to be enough for us, for our purpose now, okay? Now we can define, say, Baire-Green's function. Baire-Green's functions will be denoted as G0, just like the Baire parameters, and this is a function of x1 to xn, and then the Baire parameters lambda 0, m0, and epsilon, and that's going to be given by a path integral of the Baire field, the product of the Baire field and e to the power and the e to the power minus s, where s is the renormalized action, which has a renormalized Lagrangian, and that is given by half del mu phi 0 del mu phi 0 plus half m square phi 0 square plus lambda 0 by factorial 4 phi 0 to the power 4. Now, although these are the path integral is being done with the right action in the sense after adding the counter terms, but the factor of fields here, these are bare fields, and therefore they are supposed to be divergent. This result is supposed to be divergent. Bare fields are divergent. So when we say that Green's function are finite when evaluated using the modified Feynman diagrams, these are the properties of the renormalized Green's function. If you just replace everything in the usual Green's function you can replace every object by the corresponding bare quantities, that doesn't give the finite contribution. So these are not the right kind of Green's function that we should be looking for. What we should be looking for is a renormalized wave functions, renormalized Green's functions, and such that which are guaranteed to be finite, and those are the ones which have instead of phi-zero factors here, we should have phi factors, right? That will be the right Green's function. When we calculated Green's function so let me first write and then explain it further. The reason why this should be finite, and we should call this as renormalized Green's function, is the following. When we first defined the Green's function, we took the same thing but with L renormalized replaced by the original classical Lagrangian, and that gave divergences, and we corrected them by counter terms, and those counter term diagrams, and those diagrams are produced by counter term added to the original Lagrangian, and that is what the renormalized Lagrangian is. So that means that process of the adding counter term and making the Green's function finite is equivalent to calculating this object, where we have not phi zeros but phi's, but the path integral is being done by the renormalized Lagrangian. Okay, so this is the renormalized Green's function, and this depends on the mu in two ways. One is that there is an explicit mu dependence because it is explicitly appearing here, and there is implicit mu dependence coming from the implicit dependence of m and lambda on mu. Okay, So this has both and this implies that G0 is same as z phi to the power n by 2, because you are relating this each phi 0. So phi 0 is equal to, recall the definition, the relation, phi 0 is z to the power z phi to the power half times phi. So that relation is being used to write G0. The n factors of phi 0 that is present in G0 is being replaced by z phi to the power n by 2 times n factors of phi's, and that is the renormalized Green's function. Then, once we know what this bare Green's functions and renormalized Green's functions in terms of the path integrals, which is that's what we just did. Once we have that, we can define the bare and renormalized 1pi vertices in terms by using the relation of those vertices to the Green's functions. So for n equal to 2, one should have ddz G connected bare 2-point function x minus z lambda 0 m0 epsilon times gamma 2 bare z minus y lambda 0 m0 epsilon. This must be proportional to delta x minus y. And since this is same as z phi to the power half, we just got the relation between bare Green's function and connected and renormalized Green's function. Then it shows that the bare 1pi vertex 2-point must be equal to z phi. Sorry, this is not half, this is 1, because n by 2, n is equal to 2. So this is z phi inverse of renormalized 1pi vertex. because renormalized 1 pi vertex satisfies the same equation with G0 replaced by G, right? So what is G and G0 and gamma 0? The equation that G0 and gamma 0 satisfies, the same equation will be satisfied with G and gamma. And if you scale G by a factor of Z phi, then the gamma will be scaled by a factor of Z phi inverse, right? Because the right hand side is same, delta x minus phi. That is the reason. So we get this relation between the bare and the renormalized 1 pi 2-point function. For general n, we again use G connected bare n-point function x1 to xn lambda 0 m0 epsilon. The first term in that du1 to dun gc bare to x1 minus u1 lambda 0 m0 epsilon and so on. There are n factors like 2-point factors, and then gamma n bare u1 to un lambda 0 m0 epsilon. Now we have found that this is same as z phi to the power n by 2 times the renormalized one, and right, and these n factors will be given by z phi to the power n times the renormalized Green's function, and that allows us to write this connected Green's function, I mean renormalized Green's function, will have the same relation with the renormalized 2-point functions times the renormalized n-point vertex. So this each 2-point function will give you z phi times the renormalized 2-point function, and so that means we must have gamma tilde in I mean, I'm writing this in the momentum space p1 to pn lambda 0 m0 epsilon should be equal to z phi to the minus n by 2, because there is a factor of z to the power n from here, and there's a factor of z to the power n by 2 from here. So this expressed in terms of the renormalized quantity will have a z phi to the power minus n by 2. Okay, this is how the 1 pi vertices must be related. So what one finds, basically the observation is that the bare Green's function, their bare Green's function is given by z phi to the power n by 2 times the normalized Green's function, but the bare 1 pi vertex is given by z phi to the power minus n by 2 instead of n by 2, which is minus n by 2 times the renormalized 1 pi vertex. And that's true for both general n and for n equal to 2. Okay.